We discussed about mechanical properties of materials in the last class, and with some considered relationship in the sense that the relationship between stress and strain. We discussed about Hooke's law, right? Today we are going to take it forward and discuss it in a little bit more details, and then we'll go and develop strain energy equations. Remember that the strain energy equations are one important part of this course, and you have to probably start understanding and learning how to develop the strain energy for a given kind of materials or for a given structure or member. All right. We discussed this that the constraint relationships comes where we want to relate stresses and strains, and therefore there are 6 unknown stresses and there are 6 unknown strains, and you have to relate them using constitutive relationship. For this course, we don't deal with exactly 6 by 6, but we deal with stresses with strains. So 1D stress with 1D strain. So that's what we do, sigma and epsilon. And we say that they are related by Hooke's law with a proportionality of constant epsilon E, which is called elasticity of the matrix of the system. We'll discuss that a little bit more in next. So the constitutive relationship exactly is the relationship that deals with stress and strain. So there are 6 unknown strains and 6 unknown stresses. How do you relate those two properties of material, stresses and strain, by a matrix? Definitely stress is a matrix, strain is also a matrix, so it has to be related with a matrix, right? And there are 9 components on this side, right? And 9 components on that side, so there should be 81 components here, and those 81 components are all material properties, right? Each one of them represents a different kind of material properties. We'll discuss this probably in the next class in more details. And how do we bring that 81 of them, 81 of them to a very low number of 2 only, right? So two numbers for our case. Okay, so we'll discuss on these things probably in the next class, but that's how it is. So stresses, we have 9, so you have 3 cross 3 here, right? Strain also we have 9, so they're also 3 cross 3. So your constitutive relationship should be 9 cross 9, right? It should be 81. Okay, so this is sigma is equal to C. Right? That's a constitutive relationship in overall. So this is 3 cross 3. This is 3 cross 3. And how do I write this? Is it 3 cross 3? No, it's yeah. Sigma x, sigma y, tau x, y. It's not, it's actually sigma x, tau x, y, tau y, sorry, x, z. Right? Similarly, I can write that way. Okay. So what we do is we don't write it this way because this is a matrix. It's not a matrix tensor relationship. We write it in a vector form. So this 3 cross 3 we'll write like this. Let me take another page here. We write sigma is equal to sigma xx, tau xy, tau xz, tau yx, sigma yy, tau yz, and then tau zx, tau zy, sigma zz. Right, and the stress matrix is also something like strain matrix is also something like that. It is epsilon xx, okay, gamma xy, gamma xz, and then gamma yx, epsilon yy, and gamma yz, right? And here it will be gamma zx, gamma zy, and epsilon zz. What we do is we write this in a vectorial format. Nine unknowns, so we write it as sigma xx, sigma yy, sigma zz, tau xy, tau xz, tau y x, right? Tau yz, tau zx, tau zy, right? And then we will have something here, which let us name it as C. And here again, you get epsilon xx, epsilon xyy, epsilon zz, and then gamma xy, gamma xz, gamma yx, gamma yz, and then gamma zx, gamma zy. Okay. So this is 9. This is also 9 cross 1. So this has to be 9 cross 9. So this C matrix actually relates each of these stresses with all the 9 strengths. Okay. Similarly, sigma y will be related with the second row here with all the 9 strengths. Tau zx will be related to the last row here, 9th row, with all the 9 strengths here. Okay. So that's how you relate. So there should be 9 cross 9 unknowns in the C matrix. Okay, so this 9 cross 9 should represent something in the material property, some property of the material. And we don't know many of them. As far our understanding goes in material science now, many of these things are not known to the scientific world or the engineering world. So we do a lot of approximations, and one of the lot of approximations, some of them are proved through theory, through experiments that they are true. Some of them are not very crude approximations. They help you to reduce your problem, but the accuracy won't reduce much. All those things, right? One of the approximations we already know is tau xy is equal to tau yx, tau xz is equal to tau zx, and tau yz is equal to tau zy. Right? The complementary shears and the cross shears are equal. Right? So this say 9 will reduce to 6. And here also this 9 will reduce to 6. And then you don't have 9 cross 9, you have 6 cross 6. So 81 reduces to 36. Okay, so this way, this way we can reduce a lot of things, which we will talk about in the next class. In this class, we will learn about only the 1D problems. So in a single dimension, okay, not right. It's not right to write there. Probably I'll write here in a single dimension. Why is this happening? In a single dimension, there is only one epsilon that should be equal to E into strain. Okay, this is what we do. So how do we get this? We discussed that in the last class. So you have a material, you get a material like this or like this, dog bone specimen we call it, and that should be according to American standard of testing and measurement. You make a sample and then you start pulling it. So there is a tensile load, right? Test sample under tensile load. So you start pulling it, put it under UTM. We have shown a video also in the last class, and then start pulling. What happens when you start pulling, and then what you do is you start getting this diagram when you start pulling it. So you're giving some load, or sometimes you can give deformations or the strain in the material itself that can be given to the machine. And then you start pulling. So at 0, when there is no load and there is no strain in the material, the stress developed in the material is 0, right? So 0 at 0, it is 0. Then what happens as you keep on loading it slowly, it shows a very linear line here. And then if you see here, the line starts slowly to bend. Okay, take a curve. it will actually go to upper yield point and then come down to a lower yield point. But that is not true for all materials. It's true for only a few materials, for example, steel. So it will go like this and then come down like this. Okay, but that is not true for all materials. Okay, so but few materials show it. So this is called upper yield point. So this is actually upper yield point. And this is actually lower yield point. Okay, that is upper yield and lower yield. So the material will go slowly like this. So as you keep on giving load on the material or keep on giving strain to the material, the stress will go up slowly, 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 and it will behave very linearly, right? So there will be a linear relationship here till a point. It will show a linear relationship. Okay, so stress is proportional to strain, right? So this till this point, it is proportional to strain, and that points this region. And as long as it is proportional, we call it is within proportionality limit. The point, you won't get an exact point. The point where it will start losing its proportionality, right? That means stress is no more linear to strain. That means there is a curvature that is coming. You see here there is a curvature that is coming. So beyond that, that's the proportionality limit. Beyond that, it's non-proportional. And then there will be a point where, okay, now till this proportionality, what happens if I load it like this, and come here and release the load, I unload it slowly, slowly, it will start coming back to 0 point again. Again, you load a little bit higher and unload it, it will come back here. You keep on doing it. After a point of time, it will not come back. It will start going like this. It will start having a permanent deformation. Okay, it will not come back to its zero deform configuration. So that point beyond which it will start having some permanent deformation and it will not come back to its zero initial configuration, we call it elastic limit. Okay, so elastic limit is the limit beyond which the material will no longer remain elastic. In a sense, it will no longer come back to its zero position. Okay, so that's elastic limit. For many of the materials, mostly many of the metals, your proportionality limit and elastic limit are same. You won't find a difference between them for most of the cases. Okay, right? So material within elastic limit can remain linear and can also be non-linear because the linearity depends. So this is a very special distinction. Please understand. This is a very subtle distinction that a material can be linear elastic, a material can be non-linear elastic. Okay, when I say a material is linear elastic, that means it is within proportionality limit. When I say a material is non-linear elastic, I mean that it is beyond proportionality limit but within elastic limit. Okay, so this linear and non-linear term relates to the stress-strain relationship, whereas elastic limit relates to the material's behavior to come back to its original position. For example, rubber, if you take rubber, it is very much non-linear. Stress-strain relationship is very much non-linear, but it's very elastic, right? It comes back to its initial configuration. But if you plot the stress-strain relationship, that will be very much non-linear. Okay, but for many metals, mostly all metals, your proportionality limit and elastic limit are same or considered same. Right? So now what happens? It goes up, 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 and then there is a point where it will start coming down. So the point from where it starts coming down, it's called the upper yield point. What happens now? The material starts showing some plastic flow within it at the upper yield point. So it will start showing upper yield point, it starts showing plastic limit, and then it will come down and then it will flow straight. That means your strain is increasing, but there is no stress that is developing in the material. This is not this big, it is drawn in exaggerated format in this figure, but it's not this big. It will be a very small portion like this, maybe, or maybe like this. Okay, many material will not show it also. Many metals will not show it also. So this is called where it yields. That means where it is having a start of having a plastic behavior. Okay, and then after a plastic flow, it will again start getting some stresses. Okay, and while getting some stresses, what it will do is it will harden itself. I'll talk about state hardening a little later, but what happens, it starts hardening itself. So it goes, and after a point that is called ultimate stress, is the maximum stress that it can take, it will start showing necking. Okay, that means its configuration will start growing. So necking will start here also. Slight necking, you can start seeing slight necking from this point itself, from the this limit, from this limit point itself, and then it will start breaking here. So your necks will start breaking slowly, and then at this ultimate point, the fracture point, it will break completely. Okay, so here is a complete story given for the material. The picture is a little bit exaggerated. Okay, and there are various values of sigma given. So this is called sigma proportional. This is called sigma yield. Okay, this is what we consider as the strength of the material, sigma y, and that's not the upper yield point. That's the lower yield point. Okay, it is not the upper yield point. It's always the lower yield point. For materials which shows both, many material will not show both. Okay, lower yield point. Okay, so that's the lower yield point, and this is called the strength of the material. So in design, we consider that if my design stress crosses sigma y, the material will start failing. And then there is this called sigma u, which is the ultimate stress, and there is this called sigma f, which is the fracture stress. Okay, we never in our design cross ultimate stress. So the design standard, your books or the design considerations will tell you whether to consider sigma y as your limit or sigma ultimate stress sigma u as your limit. Okay, that will be given to you, and it is a problem specific also, application specific, material specific. Right?
Hello, sir.
Yes.
Sir, you told that if we stretch a material at the yielding point, it will come back to a residual stress, something, right?
Not at yield point.
No,
Elastic
means
limit.
after elastic limit, right? Anywhere in yielding.
Yeah, after elastic limit, it will not come back to its original point.
Huh. So after yielding means the lighter grain and of the dark grain portion, if we stretch and we remove that, then also it will come to some point on the x-axis.
Yes, but with a permanent deformation.
In that time, okay, okay, sir.
Okay, but generally for metals, these points are very near to each other. These points, you cannot distinguish them in experiments. You cannot at all. So they're very near to each other. So most of the cases we assume sigma PL is equal to sigma Y. Okay, we don't distinguish between them. That's what I said. The elastic limit, proportional limit, and yield stress, we don't distinguish. We keep them same for most of the materials. Right. So this is what I discussed. Okay, the elastic behavior. So the behavior within which the material, will come back to its own position is called elastic behavior. Right. So this is linear elastic, is where we can use Hooke's law. So Hooke's law tells that as long as your material is within proportionality limit, as long as your material is within proportional limit, the stress in the material is directly proportional to the strain of the material. And the proportionality constant is called material elasticity. Okay, it's called material elasticity E. Standard, it is used all over the world with the same same variable E. Okay, so it's called modulus of elasticity, Young's modulus in some cases, and its value for different material will be different. Okay. Right, we will talk a little bit on this probably towards the end of this class, discuss about it. Now, what is proportional limit? What is elastic limit? I've just discussed these things. Proportional limit is till the point where stress and strains are linearly proportional, and elastic limit is till that point where if you leave the material, it will come back to zero position. Yielding, a slight increase of stress from this point, it will start flowing. Okay. There won't be any deformations in the material. There won't be any stress in the material, but there will be large deformations in the material. Okay? It will start flowing. Then plastic behavior, I have discussed that also. It's written here. What is plastic behavior? Remember that Hooke's law is not valid here. Hooke's law is not valid after proportionality limit itself. Then strain hardening, I'll discuss that now. And necking, we have discussed in the last class. Necking is the phenomena where the diameter or the area of the cross section of the material start decreasing. We have seen that in the experiment, right? So it will start decreasing. That's called the necking, because our necks are also smaller diameter than our head. So start decreasing, and after that it will start failing. Right? There will be sudden fracture and it will break. So necking is the point where you can start seeing the material is about to go and fail. So you don't load anymore if you want the material not to fail. Here are a few stress strain diagrams. For low carbon steel, you can see an upper yield point, and then there is a lower yield point that you can see. And you can see the proportionality point is very small, and it goes like this. Same here for aluminum, you won't even see the upper and lower yield points. You won't see a yield point at all. You will see that there is a increase and then it goes. So this kind of materials, what we do, we get something called 0.2% proof stress. Okay, that's what we find, 0.2% proof stress, and that becomes your yield strength. It should not be 4, it should be 2, 0.2% yield stress. Okay, now this is rubber. You see, there is no proportionality position itself. You don't see any proportionality, or maybe very small here. And then it shows a very nice nonlinear curve, nonlinear stress deformation, right? Stress strain relationship. But even if you release it here, it will come back. It may not follow exactly this curve, it may follow some other curve, but it will come back to its zero. Right? So these are called nonlinear elastic behavior, which is very evident in rubbery materials. Apart from, I talked about rubber, or these are called ductile materials, which show necking and yielding. There are materials which are brittle materials, which will not give you any information or any intimation of necking. It will just go from its linear position and then break. Okay, so neither you see any yielding, neither you see an ultimate stress, neither you see a flow in the material, plastic flow in the material, nothing you can see. It just breaks. For example, as I told you last time, you take mud, right? You soak mud in water and then solidify, and you crush it from the top. It will take some load and suddenly it will crush. Like concrete also it happens. So that kind of materials are called brittle materials because it doesn't show any kind of sign of failure. For metals, we at least see a sign of failure. So if you go and see a metallic structure and you can see there is a necking happening in the metallic structure, right? You can at least say that the material is going to fail. No, don't load anymore. That safety feature is not available with brittle materials. It will suddenly crush and suddenly breaks. Okay, so these brittle materials they have a different sigma y for tensile and for compression. Brittle materials are very good for compression because they can take compressive loads. They are very weak in tensile. Okay, so that also I think discussed in the last class. There is a figure probably somewhere. Yeah, this is the figure. So brittle materials show different characteristics under. So for them, compression is positive here. So compression is positive plotted here. You can see that strength under compression is quite high than strength under tension. So most of this material, we assume the tensile strength is 0. For example, concrete, even mud, okay, soil, we will assume that their tensile strength is very 0, but they have a compressive strength. These are mostly brittle materials. Okay. Okay, now let's get back. What is strain hardening? We said that we will discuss this. So you start loading a material. Let's say its elastic limit is this point, and beyond that, this is plastic. So I will load the material, I'll go up to this point and leave it. What will happen? This is the loading. It will unload, right? It will unload to the 0 position because it is within elastic limit. But let's say next time I load it, this is my elastic limit here. Next time I load it, I go past the elastic limit to a point B and leave it. What will happen? It will not follow the same path back. What it will do, it will follow a straight line back to this point, and this straight line will be tangent to the initial curve. So the material, instead of coming back to O, it will come back to some point called C. And then therefore the material has a permanent deformation here, permanent strain. That means there is a permanent deformation here. The material will never come back to zero. Now if I start loading from here again, in the sense that zero loading was there. Now if I start putting load here, it will start going here like this and then follow this curve. It will not come back here. It will start going like this and follow this curve. Okay, this is what is discussed here. Is it understandable? Did you understand this, or do you have any question?
Sir, you had mentioned the unloading line will be tangent to the curve. Where is it exactly tangented?
Yeah, so this is the initial tangent, right?
Yes.
It will come parallel to that.
Okay.
So if there is an initial tangent here, it will come, this line will be parallel to that line. Because your strain hardening doesn't change your E, the E remains same. So this E and the initial E, whatever the material had, will remain same. So if you don't have any question, I'll go to the next curve, which will explain this better. Strain hardening. Now you see, forget this part of the curve, okay? Forget this. I start loading the material, zero load, it has a zero strain, and it goes up, 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 up. It goes to a point where it starts yielding. It comes to a lower yield point, and then again it follows the natural pattern, right? Now let's say I take the same material and I load it. I load it, I load it, I load it, I load it. I see this curve, and then this comes down, and then it goes here, and up to this point I go, and then I start unloading it. I take out the load. And I come to zero load slowly, slowly. What it will do, it will not follow this curve. It will come like this. And at zero load, when there is no load on the material, it will show this point. So instead of coming to O, it will come to F. And this is actually your permanent deformation in the material, permanent stretch in the material. Now, again, you start giving load, right? So if you start giving load, it will not start here because it has a permanent deformation. It has a residual strain in it, right? There is some strain that is developed already in the material. So it will starting from here, and it will go like this. And this curve are parallel because strain hardening never changes E. Please note this, strain hardening never changes its elastic property. So it will go straight from here, and it will join this curve, and it will go like that. So earlier the curve was like this, and now the curve is, I can draw with red, and now the curve is like this. Okay, so if you see this material, it is linear elastic to a higher extent than this. Can you see the yield point here was up to this point A, probably. The yield point here will go up, right? Maybe near the fracture point, near its ultimate strength. So I've changed sigma y to a higher value. Therefore, I have hardened the material. The material now is more stronger, more strength. So this is called strain hardening. But the strain hardening, you lose also something. For example, here it used to show a safety catch that there is a yielding starting and the material will fail. That safety you have lost. So it is more hard, but it has become brittle also. So it has lost its ductility and it has become more brittle. Okay, but it gives you more strength also. So this is what is written here. Material start losing its ductility and it becomes more brittle. But it will be more strength there also because it's sigma u. Now its sigma y has changed from a lower value to a higher value. You can load it more. This phenomena is called strain hardening. And we nowadays, with increase in manufacturing capability or the high standard of manufacturing, we can strain harden many materials. And we use them for our industry also very, very heavily strain hardened materials. Okay, I'll stop here. And then if you have any questions, I would love to answer.
Sir?
Yeah, if you have any question, please.
Sir,
Now we are into stress strain diagram. So if you have a linear elastic material, the diagram will look like this. If you have a rigid material, there is no strain, right? So it will be just this y-axis. You keep on loading it, it will take the loading, that's all. If you have perfectly plastic material, then there is no linear part, right? It will just start like this. If you have rigid and plastic model, then rigid part is this, and then the plastic part is this. If you have elastic plus perfectly plastic, then this is the elastic part, this is the plastic part. And if you have elastic plastic model, then this is the elastic model, then the plastic parts add to it. Now, why I'm showing this all this? Because many of your materials will not show exactly this curve, but they will show near curves, right? So if you see some design which is like this, for example, this one, this curve, okay? So you will try to draw it like elastic and then perfectly plastic and then plastic part. This one elastic and then plastic, right? You will try to model it like this. That's because modeling becomes easy if you have this relationship, these simple relationships. So these are the simple standard models to capture the stress and relationship of various kind of more materials that you test regularly. But these curves you should remember, how does they look like? These are very easy questions for objectives. Now there are two things you have to understand. One is engineering stress strain diagram, and there is a true stress strain diagram. As I said, as soon as the making start, the area of cross section will reduce, right? And if you reduce this area of cross section, then load is same, area of cross section reduced, meaning your stresses will be high. Whereas in engineering stress strain curve, you don't reduce that area, you divide your load by a proper area A0, which was in the initial gauge length L0. Whereas for a true stress strain, you divide with the actual real time A. And therefore, you will see the true stress strain curve will be lower because it will always predict to low area stress because of high area. And your true stress strain curve will not show that. So it will show something like this. It is not easy to measure your real A in the sense the change while necking, the change in area, because as you go to measure it, it might disturb your experiment if it's a contact based. Okay. So you need to be careful. So always we can do this, and then we can use a formula for change in area, how the area is changing. We can have a formula for that, and then we can calculate the real area, and then we get this curve. Okay, that's the difference between true stress strain and true engineering stress strain curves. As we discussed, there are two kinds of material. One is ductile material and one is brittle material, and you have to be careful. Both are used for engineering applications. Brittle materials are mostly used to carry compressions, and whereas ductile materials are used to carry tensions. It's a general distinction. You can, based on your experience, based on your application, you might mix them and use something different. Okay, so different materials are used for different applications. That's the whole point of this. And the failure criteria are also different. As I showed you, ductile material will show you necking, show you a proper, safety features before they break, whereas brittle material will show nothing. It will just crack. So it will be a little bit more cautious with brittle materials. We discussed about 0.2% proof stress also. We discussed about compression thing. Now we will talk about strain energy. Before that, I'll stop and ask if you have any questions.